This is section 1.1, Sets Review. In this video, you're going to learn how to use some set notation to denote subsets and elements of and complements of sets. And we're also going to work with some operations on sets, which are intersections and unions of sets. There should be a review from Algebra 2. You probably have seen some of this before when we're talking about functions. And it's going to be very crucial for us to understand how to work with sets when we start talking about the description of functions later in this unit. So the basics. A set is a collection of objects. It could be anything. It can be numbers, it can be people, it can be letters. Generally, when we're talking about math, we're talking about a set as a collection of numbers. And those numbers will all have something in common or pertain to a specific function. Each object of the set is called an element. A set is named using a capital letter and is written with its elements listed in braces. Now, order does not matter. It does not have to be alphabetical. It does not have to be numerical or anything. Also, you should note that the braces are curly brackets. They're not parentheses, which is something very different, which we'll talk about in the next video. When each element of a set is listed out individually, it's called set notation. So, for example, and I want you to put this first table in your notes, is if we have this table and I say if I have a set C and I'm going to say, well, that set represents the pages of a chapter book, and I'm saying, well, those pages go from 35 to 40, so I can list out each one of those pages individually. So it's 35, 36, 37, 38, 39, and 40. Or if I have another set, for example, and I'll call it set A, and it's a set of all students who got an A on the most recent test that was given. And so that set A can contain 3 students who did really well, and their names are Olinda, Mario, and Karen. And then if we skip to the bottom one where it says the set N, where that is the positive odd numbers, if you notice, it starts at the first number that's positive and odd, which is 1, and it goes 1, 3, 5, 7, 9, 11, 13, but then you see these 3 little dots right here, and those are called ellipses. And what that means is that this list will actually continue forever without n, because there is no end to the list of positive odd numbers. Another important piece of information that we need to know is that if we're ever going to talk about any specific element in the set, we can talk about it in terms of notation. If I wanted to say that Mario is an element of set A, I would write that Mario is an element of A, and the symbol we use for element is actually this little e, it's the curvy e, and it translates to is an element of. Is an element of. And so we read Mario is an element of A. So let's try a couple examples. So using set notation, we're going to write the elements of each set, and then we're going to determine whether the statement that I give you about that set is true or false. So if I say n is the set of whole numbers greater than 12 and less than 16, I would start by writing, well, I have a set, and I'm going to call it n. I'm going to make some curly braces. I'm going to say, well, it's the numbers greater than 12 and less than 16. So the first number that's greater than 12 and less than 16 that's a whole number is going to be 13. And then the next number up would be 14, then 15, and it's less than 16, so it can't include the 16, so it would actually be a set only containing these 3 numbers. And then if I look, since 15 is in the set here, I can say, yes, 15 is an element of n. If I wanted to try another one where I said, well, if I have the set V and I'm calling it the set of vowels, well, you guys should all know your vowels. Well, V is the set containing A, E, I, O, and U. We're not going to consider Y in this case. And if I'm asking is G a set or an element of the set V, well, since G is nowhere to be found in this set, I can say no. G is not an element of V. And the way we denote not is usually just by putting a slash through it, the same way that you say things are not equal, and that will help us out. Try these next 2 on your own. Okay, so we're going to move on to some more specifics with sets. These are sort of the building blocks. So we're going to talk about subsets and complements. So first off, subsets. To be a subset literally means to have every element of one set contained within another set. So a really useful diagram that you're going to want to get into your notes is this Venn diagram here, because it has pretty much everything we're going to talk about in the next little section. So if every element of B is also contained in A, then B is called the subset of A. Meaning, if you look at the picture, if this circle here represents circle B, or set B, if I notice everything that's inside B is contained within set A. And so I can say that B is a subset of A. We also have some notation for it. It's read B is a subset of A, and this circle here, or this little C, translates to is a subset of. You might notice that it kind of looks like a less than sign. That'll probably be very helpful for you. Just in the same way that the C always opens up to the bigger set. So if B is a subset of A, then B is definitely smaller than A, and everything that's in B is also in A. This translates to as a subset of. Now, if we start thinking bigger, if we think about just the whole rectangle in this diagram, we call that set U, and that's actually called the universal set. It contains every possible element for a given situation. So if you think about the first example or the first table where we were looking at, say, the pages in a chapter book, and I had this set C, and I said, well, it's the pages from 35 to 40. Well, I could say another set, or the universal set, would be actually the set that contains every page in the book. And so I could actually write that as, and I can list out each individual page in the book, and that would represent my universal set. And so then C would be a subset of the universal set. And in actuality, every set is going to be a subset of the universal set. So everything that every set that you're working with in a given situation will fit somewhere in the universal set. So we would say that it is a subset of the universal set. The other thing we have to talk about are complements. So the set of elements in U that are not in B is called the complement of B. So this can be written as B prime or B complement. In the Venn diagram, the complement of B is all the elements in the shaded region. So if this is B, then B complement would be everything outside of B. It would be nothing on the inside. So let's try an example with it, and maybe it'll make a little bit more sense. So if I have my universal set being 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then I have the set A, which is 1, 4, 5, 7, 8, 9, B is 5, 7, C is 1, 5, 7, 8, D is 2 and 3, and E is 6 and 3. So let's just take a look. If I have set B, which is going to be the set, and we already said it's the set containing 5, 7. And if I have the set A, and I know that it's 1, 4, 5, 7, 8, and 9, to check to see whether or not B is a subset of A, all I have to check is whether or not every element in B can be found somewhere in A. So if I check, okay, well, I'll start with the 5. I look at 5 and B, and I go, well, in A, is there a 5? And there is. So this one works. And then I check the 7. Well, if there's a 7 in B, is there a 7 in A? And there is one. That's right here. So every element in B is contained inside of A. So I can say, yes, B is a subset of A. Let's try another one. So state whether E is a subset of D. So I know that if I have set E, and it's really important, or it will really help you if you write these things in order. If E is the set 6, 3, and D is the set 2, 3, if I look and compare them piece by piece, if I look for the 6 is nowhere to be found in the set D. Even though E can be found right, or the 3 can be found right here, and these check, since the 6 is nowhere found in the D, then I can say, no, E is not a subset of D. Everything that is in E is not found in D. Okay? I can tell you that E is a subset of the universal set, and that's it. Everything that is in E is only found in the universal set. Okay? And then the last one we're going to do is we're going to find a complement. So the way that we do this, or the easiest way to do it, is if we think about the universal set, which was the numbers 0 to 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And I look at set A, which is 1, 4, 5, 7, 8, and 9. The easiest way to find a complement is just to compare compare A to the universal set and cross out the ones that match. And what you'll be left with in the universal set will be a complement. So let's cross them out. I see a 1, a 4, a 5, a 7, an 8, and a 9. Which means a complement is actually going to be the set containing everything that's left over. So it looks like 0, 2, 3, and 6. The last thing we have to talk about are set operations. So the way that we combine numbers with addition and subtraction, we can kind of do the same thing with sets. So the first thing we're going to talk about is something called a union. So the union of sets A and B, written A, and then this means union. B is a new set consisting of all the elements that are in either set. So we're basically taking two separate sets and we're combining them together. The intersection of sets A and B is the set containing only elements that are in both. So the only thing that they have in common. So if you want to think about it in terms of Venn diagrams, if I were to sort of make a little circle here, and let's just get real fancy with it. So let me get a cloner. So 1, 2, 3. Okay. And if I were to call this set A, and this set B, and this set A, and this set B, well then if I wanted to talk about or demonstrate what the union would look like, basically the union, or A union B, would actually just be the combination of the two sets. I would list out every single element that's in both sets combined. I don't need to repeat, especially for this middle section that crosses over, but I can list out everything that's in the two sets. If I want to talk about the intersection of two sets, you can sort of think about it like a subtraction. You're only taking what they have in common, and that would actually be A, and this means intersect B. And the only thing that we're really looking at is the only pieces that they have in common, which would actually just be the center section of the circle, or the diagram. So I would only list the elements that are in this piece here. It's going to make a much smaller set. You can think about the intersection making smaller sets. Unions are bringing two sets together, so your set should be bigger than the two original sets. So let's try an example. So if I let U be my universal set, and it's the integers from 1 through 8, and I have R as 2, 4, and 6, S as 4, 5, 6, and 7, and T is the set containing 1. So I have 3 sets. And I've given you a diagram here to sort of illustrate what it looks like. If I want to find R union S, that means that I take this set, and I'm going to combine them together. So I'm just looking at, if this is R and this is S, R union S is going to be the set containing everything that's on the inside. So that's going to be R union S is going to be a set containing 2, 4, 6, 5, and 7. And if you notice, I didn't write them in order. It doesn't really matter. And then if I want to look at the intersection of this, of R union, or R intersect S, it's actually going to be the only thing that's in the middle, which they share, which is 4 and 6. So R intersect S is just going to be the set containing 4 and 6. And then we have this interesting operation happening here. So I'm asking for the intersection of set T and set S. So if you look, set T is here, and I see set S is here, and if you notice, they don't overlap at all. And so we would say that they actually don't intersect at all, and the result of them would still be a set, but it's a special set. It's called the empty set, which we write, actually, and it wouldn't even be a 0. We don't put a 0 in it. We put nothing in it. This means the empty set. You also can see it written like this, and it is also called the null set. That is it for this video. We will pick up with some in-class practice tomorrow.